Okay. Hello, everyone. Good morning, good afternoon, and good evening to wherever you are located globally. I'm Jake Lee, an assistant professor at the University of Texas Permian Basin, and also the webinar team lead for the SEG Early Career community. So I'm so honored to welcome you all to the SEG Early Career community's second webinar. So we are truly excited and glad to have everyone joining us today for this event brought to you by SEG. Just before we start, uh, uh, I'd like to briefly introduce our early career community. So early career community. So we are a vibrant community of over 80 young professionals globally, including students, academic researchers, and industry experts. So our mandate is very simple. So ECC exists to provide a vibrant and supportive network for all SEG early career members, and we aim to foster meaningful connections, support professional development, and encourage active volunteerism across SEG's various committees and programs. Before we dive into today's topic, so I just want to give a quick heads up on our next major event, the Early Career and Student Global Workshop. So the workshop is titled Projecting the Future of Subsurface Characterization with Seismology, and it will be held virtually from June 29th to July 2nd, 2026. We encourage you, all early career members and students, to submit your research abstracts. The call for abstracts opens on December 1st and closes on January 15th, 2026. And I'd like to make sure, so this is a fantastic opportunity to present your work on a global stage. So please visit the SEG website for more detail. And also, we are looking for sponsorship. So if you are very interested in sponsoring this workshop, please contact Mallory Trombor via this email address. And if you are not yet an active member of the early career community, please consider joining us. We welcome students and young professionals from all areas of applied geophysics. Please feel free to scan this QR code on your screen. And now, for the main event, today our webinar is titled Key Factors in Making a Revolutionary Change in Passive Seismic Monitoring Using AI. Our distinguished speaker is Dr. Yang Kang Chen, team lead of Machine Learning and AI Research at Texas Seismological Network, in short TexNet, Bureau of Economic Geology, UT Austin. Dr. Chen graduated from UT Austin with his PhD in geophysics in 2015. And after his postdoc at Oak Ridge National Lab and assistant professorship at Zhejiang University in China, he joined UT Austin TexNet Group in 2021. And now he's team serving as a team lead of AI machine learning research for both Texas Seismological Network and TCCS groups at the Bureau of Economic Geology. So his AI system has been deployed and is now the baseline model for TexNet analysts, significantly helping to reduce manual workload and improve analysis quality. So we are delighted to have you, Dr. Chen, guide us through your transformative research on this topic. And also, please feel free to post your questions in the Q&A section, and Dr. Chen will address them after his talk. Dr. Chen, the floor is yours.
Thank you, Jack, for your introduction. Hello, everyone. Today I'm going to present some of the research we have been doing in the past decade on making an AI application for earthquake monitoring from infancy to real-time in production, everyday running. The key point is to make a revolutionary change using AI, you really need to be patient because it takes time, it takes effort, and you really need to have a patience and persistence to see it happen. A brief introduction of myself. A brief outline of my talk. First of all, I'd like to acknowledge a number of people who made a significant contribution in this workflow. Without their effort, this presentation is just impossible. And then I will present to you several best figures showing the magic of how AI can make a revolutionary change for our everyday earthquake monitoring. And then I will guide you through a long journey, a decade-long journey, to put AI from infancy to production for earthquake monitoring. And then I'll show you tons of sensitivity tests, benchmark tests, to kind of let you know this is indeed a revolutionary change. And lastly, I will draw some conclusion. So first of all, I'd like to thank a number of people who made a significant contribution in the past decade. These people are current colleagues, past students, and past postdocs working with me and in my group to make this AI magic happen. And I'd like to thank all of them. Before guiding you through the long journey, I'd like to show you several really groundbreaking results using our in production daily operating earthquake monitoring framework. So as we can see from this slide, we have an area of interest in West Texas, where we have most of the seismicity, mostly injection-induced seismicity. Most Texas seismicity also located in these areas. We call it like Delaware Basin and more broadly speaking, the Midland Basin, right? We select one areas for having some statistics shown on right-hand side. And on the top right, we show the magnitude difference distribution. So the magnitude difference also magnitude error measured by calculating difference between AI magnitude and the manual magnitude. Well, we can see most of the magnitude errors are just around zero, very close to zero. And on the bottom right, we show a plot showing the comparison between the magnitude of AI and the preferred magnitude from manual effort. The key point here is that for magnitude above 2 earthquakes, we have like recall of 100%. So we do not make any mistake for magnitude above 2 earthquakes. So this is very magical. And next slide show the step-by-step change in terms of the detectability using our AI system. In this figure, on the top left, we show 3 scenarios. As we can see, we have 3 colors: red, yellow, and gray. The red denotes manual effort, which is enabled by our TextNet analysts. And this yellow one corresponds to automatic method. Many of you may know it is SDA-LTA, an optimized SDA-LTA method. And this gray one is the deep neural network. Right? And I call these 3 scenarios 3 eras: the era of manual effort, the era of automation, and the era of AI. If you are familiar with AI, you know that automation belongs to AI. So when we enter this era, we already enter the era of AI. But the AI we are mostly talking about nowadays is mostly referring to the deep neural network-based AI. So throughout my talk, AI and deep learning, they are the same thing. Right? On the top right, we show a daily distribution of detected earthquakes from around 7 to 8 earthquakes detected per day manually to around 60 to 70 automatically detected earthquake per day to nowadays 300 and 400 automatically detected earthquakes by deep learning. So that's a step-by-step change, very magical. And on the bottom, we show the magnitude distribution on a daily basis. Well, we can see beautiful distribution of different catalog. Right? For the red one, mostly are large earthquakes above 2. And we can see a particular day here because we have a very high magnitude 5.4 earthquake happening in West Texas. And we see that right after this large magnitude event, we have tons of small earthquakes. We also see tons of small earthquakes before this large magnitude event. And on the other hand, we see that most of the deep learning catalog, they are mostly residing in this area, this very small magnitude range. And from this slide, I will guide you through a long journey, putting AI from infancy to production. But first of all, I'd like to show you the problem we are solving. The problem we are solving is quite straightforward. So suppose we have a 3-component seismograms. All we need to do is to detect a P wave and S wave from these 3-component waveforms. We can either, who's controlling the, sorry. Nope. Please do not move forward the slide. Someone is controlling this slide. It's not me. What happened? All right. So the problem we are solving is really to detect the P wave and S wave, right? Using whatever method, using HTA, LTA, clustering, or deep learning method, right? As long as we get the P wave and S wave arrival from these 3-component waveforms, the most manual effort intensive step is done, and we can go forward to other steps. Next, I want to tell you some background story about this type of research. So the current ongoing AI boom really started in early 2016, where the famous company DeepMind made a stir to the world that they are. Oh, please don't move the slide. What happened? Someone is moving the slide. Please do not push the previous and next button. No, what happened? What
It's
happened?
not me. Jake, Josh, are you doing this?
Who is moving forward the slide?
I'm not quite sure, but please stop moving the slides. It is, if you can hear us, please stop moving the slides. Which slide do you need to be on? The 14?
Wait. 14. Yeah, 14. I think 14. Yes.
Okay.
Yeah. So the DeepMind made a stir by announcing their AI player.
Moving the slides. Are you moving the slides now?
No, I'm not moving.
No, who's moving the slides? Whoever's moving the slides, please stop doing this.
Okay, Sim, stop. I'll keep moving.
I'm gonna push your slide again. Okay, not quite sure.
Oh, I keep moving. Keep moving. Here, yeah, stop. Right. So this news, I bet most of you know this news. So I'll just skip this, right? Because of this news, the whole world is very excited about the AI. So did I. So that brought us to the first factor to make a revolutionary change in passive seismic monitoring using AI, a strong scientific motivation. Back in the day, I was doing a postdoc at the Oak Ridge National Lab. Some of you may be familiar with the supercomputing power at the Oak Ridge National Lab. Who is moving? Back, previous. No, please stop doing that.
Mi Zhang. So your role is not a presenter. Please leave this room.
Can we kick Okay, let's move back. Sorry about the troubles.
Mi Shang, if you are the one moving the slides, please stop moving the slides. If you can hear us, please stop doing what you're doing. Only the presenter should be moving the slides. Yang, what slide are you supposed to be on?
16 or 17, I think.
16 or 17. I'm gonna push 16. And whoever was moving the slides, please stop moving the slides or disrupting the webinar.
Okay, yeah, that's good. No, stop, not me. Mi Zhang. All right. Can we just remove this?
Trying to move. How do you remove? I'm trying to remove him, but I can't.
Mi Zhang and Ming Wu, please leave this room. Your roles are not presenters. Please choose a different role to join this webinar.
The producer, Robin, maybe Robin can remove this presenter.
Robin is in trying to do it. Oh my God. Whoever's moving the slides, please stop moving the slides. When you move them for everybody. If you have noticed the webinar have stopped because you are moving the slides, would you please stop moving the slides?
No.
Okay.
Stop. Okay, let's.
I pushed. Oh God. Okay, I pushed the slide 16.
Yeah. 16. Yeah. That's. Sorry for the troubles. Okay, I'll start from here. So a strong motivation for this research comes from we want to do global full waveform inversion for inverting for the global interior structure using like 3-component waveforms. And there's a need for automatically picking the waveforms. We need to pick the waveforms that have sufficiently close observed and synthetic data. And that brought me the first AI problems. To achieve this goal, I developed a quite straightforward physics-based method. I designed 5 features. As we can see, these 5 features more or less are related with the similarity between the observed data and the synthetic data. And based on these 5 manually defined features, we can define a feed-forward network where we have the input, the training samples with these 5 selected features and go through the neural network, which is like only 2-layer structure, and then we can output a label, right? And we can achieve this goal of selecting waveform. But back in the days, in about 10 years ago, we really didn't have any resources for earthquake picking or earthquake detection. So we need to develop everything from scratch, right? And this is a screenshot of the GitHub repository I developed for this purpose. As we can see, the first commit really came around 8 years ago, right? And on the right-hand side, I will show an example class for doing this task to detect the waveforms. And compared with the state of the art at that time, which is the fluxwing method, we actually did a pretty good job in terms of the waveforms, right? So for this example, we detect most of the waveforms, and in some places we are even better than the fluxwing method. But the problem for this method is it is computationally expensive because you need the synthetic data, right? For the global scale computation, you really cannot afford this level of computation. So we tried to develop a faster method. In this case, we developed the clustering-based method. The principle of clustering is that for several objects, if they are close to each other, then they belong to one cluster, and then otherwise it belongs to a different cluster. We can think the STA-LT method as one feature clustering problem. In this case, we only have one feature, right? Like in traditional method. But for STA-LTA, the feature, the vectors like this, right? Even for very small noise, it can cause this strong oscillation. And to stabilize this process, we can introduce 2 other smoother features like the mean, average power, just to make the features smoother. And based on these 3 features, we can make the peaking more stable and more anti-noise. We can apply it to different data, including microseismic data with quite a strong noise. We can get a pretty good result, for example, like this, compared with STA-LT method. And we can also apply it to other data sets whenever we need peaking. So this is just another example. And we can keep moving on, developing similar but slightly different method for different purposes. For example, for this case, if we want to detect the waveforms, and then we should not just use STA-LTA because STA-LTA is more sensitive to the first arrival. And to detect waveforms, we may use some features that are more appropriate for waveforms. For example, in this case, the spectral centroid features defined as this equation. And in this case, we are more capable of detecting the waveforms, like in this frame box zoomed here. We see that most of the waveforms are detected quite successfully. And then based on the waveforms, we can do automatic microseismic imaging for locate the microseismic event. And we can even add more features. For example, in this case, we can add close to 200 features. All these features have some statistic or physical meanings, and we are inspired from the acoustic signal processing field. Acoustic or speech signal processing, they have quite a lot of experience in dealing with speech signals. So we just use they are widely known features to help us to locate the waveforms. And as a matter of fact, it works pretty good. For this example, we can have a field data. We can prepare the labels manually, and based on the labels, we can train a model and then do picking for quite challenging microseismic data. And we can even combine the clustering method with convolutional neural network just to enhance the anti-noise ability without sacrificing the resolution, because the clustering method can really help, because it's sample-based. It can really help boost the resolution, but the CNN helps us to stabilize the window selection, right? And we can, here we show the comparison between the SDLTA and the clustering method and the CNN clustering combined method, right? So this, we just keep adding more features and more algorithms to make the workflow more stable. And here we show a sensitivity test in terms of the noise level. As we increase the noise level for different methods, we can compare their anti-noise ability in terms of the peaking error. And as we can see, a noise increase, SNR decrease, and clustering error increase much faster than the CNN clustering. Right-hand side, just an example of those peaks on the waveforms. This slide shows a principle of using time frequency transform. We all know continuous wave transform. It's a way to transform the data from time domain to time frequency domain. And in this case, we do some tests for the same data. We add different noise, right? Increasing noise. We found that for the wavelet spectrum, the difference mainly resides on the high frequency part, but for the low frequency part, they are more or less the same. So this is the principle of using a time frequency transform to help us better classify the waveforms into different components. And yeah, this is the workflow of using time frequency transform to help us better pinpoint where we have waveforms and where we have noise. What's the remaining problem after all these tests? The model is not generalizable because all the previous examples are based on small data set. But in order to make this highly generalizable, it brings up another factor, key factor, to make a revolutionary change using AI. That is a huge amount of data, like many other fields. So starting from 2021, we started a much more ambitious project. No, stop. Someone is moving. Stop moving. Stop moving. Stop moving, please. Whoever is moving the slide, please stop. No, please stop moving. Who is moving?
Okay, whoever logged in wrong in the webinar, please stop moving the slides. You are interrupting the webinar for everybody else.
Let's keep going,
What slide do you need to be on?
30 something, I think.
30.
30, how about 30?
30. Okay, I'm gonna push it there.
30, yes, more or less the same. No, please stop.
Okay, we have 2 people from On24 in here. Can somebody please kick whoever is doing this out, which I believe is 11-2 logged in as producer. I'm so sorry.
It's okay.
Really apologize. I don't
Sorry.
know how somebody got a hold of this login.
Sorry for causing the trouble.
Oh my God.
Yeah, stop. No.
No. If you are logged in and moving the slides, if you're clicking next or previous, please stop doing so. It is moving the slides for everybody else, not just for you. Yeah, I'm gonna try to push the slide 30 again for you.
Yeah.
Oh my God.
Okay, so this is correct. No. Stop. Okay, stop. Starting from here. All right, so
I'm gonna push again the slide you want to be on, which is 30th.
no, the
correct?
next one.
This
No, the next one. Next one. Next one.
Oh my God.
Yeah.
Are you
this one's
moving it
great.
or somebody else? Okay.
Somebody else. This one's okay. Oh, stop here, please. Yeah. No, I'm not moving. Okay, stop here, please, please. What happened? Uh, let's pick up. Please stop. Keep moving. They are weird producers here. On 24. On 24. Come on. Stop. Kind of. Okay, let's go back. Let's go back. No, please don't.
No, it's
All right.
just a random person.
Okay, let's start from this. Okay, so anyhow, we need a huge amount of data, and then we develop a scalar deep, and then we keep moving on. We develop this EQVIT, and then this slide shows the magnitude calculation performance for California and Texas, and we show that the predicted catalog from EQVIT and the ground truths are mostly the correct ones, and yeah, so all the previous works are based on P-wave only. So why we need a P-wave only? Because that's for earthquake early warning. For earthquake early warning, every second matters. So we really are only allowed to use the P-wave information. But for earthquake early warning, we also need a location. So we also develop a location workflow shown here in this slide. So basically, we develop two scenarios. First, if we have a huge amount of data, like in Japan, and we can use the real data to train the model. And then if we do not have a lot of real data, like in Texas, like in Egypt, we need a synthetic data, right? We can generate synthetic data using rate retracing, travel time calculation, whatever. We can generate a huge amount of data, and then we do training, and then eventually we can apply the model to a real scenario like here in Japan. We can make it work, make the earthquake location within a second. So after all this work, we finally arrive at the EcoCCD, which we use for TextNet real-time monitoring. For the whole state of Texas. That is EcoCCD. Simply speaking, why we use EcoCCD? Because it is as fast as convolutional neural network, but as accurate as a transformer architecture. Right? So that's why we use EcoCCD. What we arrive this by doing tons of tests, and this brings us to the third factor, the persistence. And we really need to be persistent and patient for a long time, right? We have done like quite a lot of work, almost trying every method we can from 2017 till this year. We've tried every method we can try, every architecture we can try. And then finally, we arrived at the point that EQCCT is the best. And here is just a brief introduction about why CCT is fundamentally better than CN architecture. We can use the face recognition as one example. For human face, for CN, as long as we have all the components, eyes, nose, mouth, we consider it as a face for CN. But for transformer architecture or any other requiring internal relationship, we not only need those components, but also we require those components sitting on the right place. So that's a fundamental difference between CN and transformer and this convolutional compact convolutional transformer. And next, I'm going to show quite a lot of experiments. So I'm going to show first the application to large magnitude events. In this case, we have magnitude 4 events. Those lines correspond to the peaks. For P wave and S wave, we'll see those two lines are overlapping with each other. That means exact correct. And for large magnitude event and for moderate S signal to noise ratio event, magnitude becomes weaker, noise becomes stronger, and we can also see the result for the low signal to noise ratio event. And this slide brings up to the force factor, the benchmark, right? Because for AI research, we are not just doing application. We want to proposing something really strong, and so we need to do benchmark to see how better our method is, and how much faster our method is. So we really need the benchmark. So based on the benchmark data set, we compare different architecture like the FaceNet, like EQ transformer and EQCCT, right? And as we can see, the errors become smaller and smaller from left to right for P wave and for S wave. For all the same data, different architecture, EQCCT just performs best. So that's how we know it performs best among most of the state of the art. And next, it brings up the fifth factor, that is teamwork. Because people joke, if you can do something alone, most likely it's a small thing. If you want to do something really big, you need teamwork, right? You need a lot of talents, a lot of people working together toward the same goal. So that is teamwork. So I have a lot of example of showing how teamwork really helps. So for such a big project, we want to make AI in production for everyday in production monitoring. We really need expertise from different aspects. For example, Omar Saad used to be a postdoc working with me in my team, and who is currently a research scientist at KAUST. He brought us the expertise of AI, right? So this slide just to show a couple of his earlier work in AI, which are all the foundation of the current work I'm presenting. And also, Professor Yun Fengcheng is an assistant professor working for Zhejiang University. He is a brilliant earthquake seismologist. He brought us the expertise of earthquake science, and he helped us do the generalization ability test to apply it to everywhere in the world, so that our method is more impactful. For example, we apply it to Japanese data set, we apply it to Texas data set, and Italy data set. All of these data sets, despite the dramatic difference, they all perform very well, right? So that's the expertise of like earthquake science. We can also do the same thing, the error benchmark for different areas for P wave and for S wave. And also, we got the help from Nadine Igning, who is now assistant professor at UT Dallas. She is expert in microseismic monitoring, especially for Talk to Me dataset, right? She helped us to validate our method in microseismic monitoring, right? Because we know that microseismic data largely different from earthquake dataset in terms of many aspects. But anyhow, we apply it to microseismic data because of some like expertise from those fields. And because of Daniel Server, who is now research engineer at UT Austin, Daniel brought us the forefront expertise for earthquake monitoring. So he helped us to make this in production, make our pure ecosystem from a pure research product to an industrial scale framework, and that is very, very important for us. And here is an example of showing how accurate the catalog, earthquake catalog generated from AI in terms of just location. And here I want to show, so the key point of this slide is for a majority of the earthquake, we make almost zero mistake, and the location error is almost zero. But only for like less than 5% of the total earthquake, we do have outliers, right? See here, because of one or two abnormally wrong peaks. So the key point is AI is powerful, but it's not the panacea, right? We really need to be careful of using AI products. And we can keep going, making a very comprehensive and effective framework, leveraging the three component waveforms, going through all the process, getting the peaks and do the association, and then do the catalog, and then we can refine the catalog. We can even do a relocation, obtaining the high resolution catalog, right? All these frameworks are just seamlessly connected to each other and making a magic. For this case, we show the comparison of locators. On the left-hand side, we show the LOCSAT, which is a location module in the SASCOM software for 3 months using our AI framework. And on the right-hand side, the same catalog, but with a different locator. We see that because of the better location performance, the catalog is just more clustered. And this slide shows the relocation comparison for manual catalog for 1 month. As I said in the beginning, manually we can detect around 200 earthquakes per month. And for the right-hand side, we use AI, we detect more than 50 times more earthquakes. If you look at the catalog after relocation for just 1 month, it's beautiful, right? And here we show an example of one event, small event, detected by TextNet and AI. But by using AI, we detect the same earthquake from more stations, right? So here, using AI, we detected the same earthquake from 15 stations, but manually we only detect the earthquake from seven stations. And we can also show a much smaller event here, around 0.4 magnitude. This quake is completely missed by manual effort, but in this case, we picked it using our AI approach. And here we also show the comparison between AI picker and the traditional picker, which is SDLTA. And here we show different colors. For those the green colors, it corresponds to the newly triggered station because of the deep learning. And because of the newly triggered station, we can get a much more balanced location located here, while the previous location is just wrong, located here. And we can also test the sensitivity to the station density. The question is, what if we don't have a dense network? How is the detectability? So the answer is, even if we have a much smaller number of stations, we can still detect a pretty good number of events. But with more stations, we just can detect more, right? In this case, 1/3 station correspond to 1/3 event. So that's an interesting test, showing the importance of the station density. And here we show the catalog after relocation in terms of delineating the fault. For example, for here, so these are the left-hand side are the longitude slice, right-hand side are the latitude slice. On the right-hand side, we can see a beautiful fault structure. And this fault structure corresponds to the fault plane of the large magnitude event, magnitude 5.4 earthquake happening end of 2022, right? So because of AI, even using 1 month's data, we can delineate the fault beautifully. We can also show the fault delineation on the map, comparing the manual effort and the AI catalog monthly distribution, right? We can see it is from left to right, it is a dramatic change. We can even do a better science by associating the seismicity with injection activity, and we have found many interesting stories, but I just skip this one. So this slide shows the GitHub repository of this EcoCCT architecture, which is the backbone module for our daily monitoring framework. A question is, can we do it even better? Right? So the answer is definitely we can do transfer learning. We can like keep refining the architecture, the model using more better compiled regional dataset like the Texas earthquake dataset. We compiled the dataset using all the efforts from all the TextNet crew in the past 7 years. Based on this newly compiled dataset, we can do transfer learning. We can even boost the performance to a newer level, right? So here is just one example showing the better detection performance in faraway station. And we can do very accurate daily operation using AI, as shown in the first slide. And very recently, this year, we are making some hardware level improvement to further improve the efficiency of all the process, right? From 9 minutes processing 300 waveforms to around within 1 minute processing the same number of waveforms by optimizing the hardware and the software implementation, right? So this is the latest work. Because of this very recent optimization, we can make the monitoring real time. The real time means we have latency of 30 seconds. So that's really a high level efficiency for earthquake monitoring. And this slide brings us to the last factor, which is coverage. Because of the coverage, we are able to make it in production, right, for a statewide seismic network, and the result is just fascinating. We obtained very robust real-time monitoring performance thanks to the coverage of Director of TextNet. So what's next? Maybe we can even make the framework better or faster, right? Please just stay tuned for more magic to come. So last slide, I want to summarize a little bit about the 6 factors I just mentioned. As we look back on the journey, 6 factors really play an important role, right? First, we need a strong scientific motivation to propel us to do hard work to be persistent for a long time. And we need a huge amount of data for making AI a reality for daily operation. And we need a benchmark so that we know how better and why we need AI, because it's not a small change, it's a big, dramatic change. And we need teamwork. This somewhat is most important thing, because we just need a lot of people working together toward the same goal to make it happen. And we need courage to make a production deployment for AI system. And finally, we need persistence. And Rome is not built in one day, so we really need to be persistent and patient to see the magic happen. So that's my presentation. I'd like to take any question.
Okay, yeah, thank you, Dr. Chen, for that insightful presentation. Okay, so before we start the Q&A, so we sincerely apologize for the slight technical issues experienced earlier, and so I think we are running a bit behind schedule, but I think we can receive a few questions now. Okay, Dr. Chen, are you ready to take
Yes. Yeah.
our questions?
Sure.
Okay.
Yeah.
The first question is, are there any differences between earthquake monitoring and microseismic monitoring? For instance, for monitoring hydraulic fracturing.
Yeah, I think the main difference is on the data difference. Microseismic really relatively have a higher frequency, and so as with the sampling rate is much higher than the earthquake. So we really need to do some careful pre-processing to make it happen, make it the earthquake monitoring framework applicable for microseismic monitoring.
Okay, yeah, thank you. And next question is, in your monitoring framework, which part requires AI and or machine learning?
A good question. As I mentioned in the beginning slides, so the only part requiring AI is the picking, the P wave and S-wave picking. So as long as we can get a good picking of the P wave and S-wave, all the follow-up procedures can be done very efficiently and effectively. So I think the picking is the only AI demanding task.
Okay, and another question is, what software do you use to associate the peaks with events?
We use well, good question. Association is one important step in the whole earthquake monitoring workflow. So we use I don't quite remember the exact name, but it's based on SASCOM. We use SASCOM for most of the follow-up procedures.
Okay, and next question is, have you conducted research on AI-based focal mechanism inversion?
Yes, we have done that. We have published a paper in last year on developing a compact convolutional transformer for picking the first arrival polarity, and then conduct the follow-up focal mechanism based on the hash method.
Okay, and next question is, can you clarify a bit on the difference between real-time monitoring and playback mode?
Good question. I think the key difference is the latency, right? So for playback mode, we can run the whole system retrospectively. So the latency can be minutes to hours. But for real time, we really need to make the latency within a minute. And also it's definition dependent. It depends on how you define the real time efficiency. So in our daily operation, we define our latency requirement as within seconds, like within 30 seconds. If you can output the peaks and catalog within 30 seconds, we can call it real time.
Okay, and another question is, what optimization method has been used in Transformer? Can the work be extended to supersphere events recorded in Myanmar?
Oh, good question. Very scientific, I think. So our network is called CCT. CCT means a compact convolutional transformer. You can consider it as a transformer, but we use the convolutional blocks, quite a smart integration of a number of convolutional blocks to extract the features so that we have a few features instead of the whole time series, so that we can make transformer faster. But the backbone of this network is transformer. We still need to leverage the inherent time series information. Regarding the detection of the super shale event, Myanmar, I think it just depends on a fairly good data set. If we can compile a data set of waveforms from super shale events, and then we can, I have confidence that we can do a pretty good job in that case.
Okay, I think this is about a following question. So regarding latency, you mentioned 30 seconds. So could you please clarify what you define as latency? 30 seconds from origin time?
All right. So not necessarily 30 seconds from the origin time. I think the 30 seconds, so in real-time system, we have to update the peaks in real time, like every second, every 30 seconds. The latency means we update the last catalog in the real-time fashion every 30 seconds. So that's a matter of like progressively updating the catalog in real-time fashion. So that's not necessarily means that after the origin time. I think that's really like real-time monitoring or real-time operating system terminology.
Okay, and so this webinar is especially for early career professionals, students, and professionals. So, as a research associate professor and well-known seismologist with among the highest citation numbers. So, could you advise on anything? So, for masters and PhD students. So regarding the usage of AI, integrating the geophysics and or seismology.
That's a good question. Real development question. I think the best advice is you need to believe something. Believe, for example, like if the research topic you are going to do is promising, right? Otherwise, you are lack of motivation, right? Maybe you can sustain for a couple of years, but you cannot sustain for like decades, 20, 30, 40 years. You really need a very strong motivation. So you really need to believe something, and you have like endless momentum to do that. And after that, if you have a very strong motivation, and you will have a lot of hard work because you want to make it happen. And then I think the hard working is just straightforward. If you have a very strong motivation, like play hard is like work hard is play hard. Right? So for you, it's not hard work anymore. It's just the enjoyable things if you believe something. I think you need to believe something, and you need to spend effort to make it happen. And then you really need to be persistent, like I said. So you need to stick to your dream, stick to your goal for quite a long time, like 10 years, 20 years, 30 years, and then hopefully you can make it. So that's my advice.
Okay, yeah, thanks so much. So I think so let's conclude the Q&A session. Okay.
Sorry, Dave. There's one question in the attendee chat, and so they wanted to know if the work can be extended to super shear events recorded in Myanmar.
I think I already answered. Right?
Yes.
Oh, okay, sorry about that. Go ahead.
No problem. Yeah, we needed a fairly good data set to study the super shear waveform.
Okay. Okay. So thank you once again, Dr. Chen, for sharing your pioneering work and career insight with our community. So now we are concluding our second webinar, and also don't forget to consider joining all these early career and student global workshop. So this is fully virtual, and this webinar will be held from June 29th to July 2nd. So our abstract submission will open in December. So please stay tuned, and please scan this QR code to get the more event information. Okay, yeah, thanks so much.
Thank you so much. Thank you for your attention.
Thank you.
Bye.
Yeah, goodbye for now.